All right, let's dive into one of the most crucial processes behind the AI tools we use every day, large language model tuning. So, what's the big idea here? In a nutshell, LLM tuning is all about taking a powerful general-purpose AI and turning it into a specialized assistant that actually understands and works towards what we as humans want it to do. To get a bit more specific, tuning is the process of adapting a model that has already learned the patterns of language. We're not teaching it English, we're teaching it how to behave. We're guiding it to follow instructions, adopt a specific tone, and, most importantly, to be helpful and safe. Now, to really appreciate why tuning is so essential, you first have to understand the limits of a model that has only been pre-trained. Think of a pre-trained model as a massive digital library that's read pretty much the entire internet. It has an incredible grasp of language and is amazing at predicting the next word in a sentence. It's like the world's most sophisticated autocomplete. But here's the catch. It isn't inherently an assistant. It doesn't automatically know how to follow your instructions, stick to a certain personality, or align with human values. That's the capability that has to be explicitly taught through tuning. And here is a perfect, almost funny example of what can go wrong. When a model that's only had some basic tuning was asked for fun activities to do with a teddy bear, this was its response. You can see that it's grammatically correct, but it's completely unhelpful because it totally misunderstands the user's intent and the desired friendly tone. And this is what we're aiming for. After proper preference tuning, the response is completely transformed. It's helpful, it's friendly, and it's perfectly aligned with what the user was actually asking for. It shows the model has learned not just what to say, but how to say it. So, how do we get there? For a long time, the dominant method has been a process called reinforcement learning from human feedback, or RLHF. Now, RLHF is a pretty involved multi-stage process. First, you collect a data set of human preferences by having people choose the better of two model-generated answers. Then, you use all that data to train a completely separate AI called a reward model. Its only job is to act as a proxy for human judgment. And finally, you use that reward model to tune the main LLM, essentially training it to produce answers that will get a high score from your AI judge. This reward model is really the centerpiece of the whole RLHF system. It learns from thousands upon thousands of human comparisons, so it can output a single numerical score, effectively acting as an automated judge of quality. The goal for the main LLM then becomes simple: get the highest score possible. But this raises a critical question. If the entire goal is just to maximize a score from this automated judge, what could possibly go wrong? Well, this leads us to the single biggest challenge with RLHF, something called reward hacking. Because the reward model is just an imperfect proxy for what humans really want, a smart LLM can learn to game the system. It finds loopholes to get a high score from the judge without actually providing a good answer for the user. It's the classic case of teaching to the test instead of teaching for true understanding. On top of the risk of reward hacking, RLHF is just operationally very difficult. It's a highly complex system to set up. You need to train and hold multiple large models in memory at the same time, which gets incredibly expensive. The whole process can be unstable, and it's notoriously sensitive to getting all the little tuning knobs and settings just right. So, because of all these complexities, researchers started looking for a simpler, more direct alternative. That's where direct preference optimization, or DPO, comes in. DPO completely reframes the problem. Instead of that complicated two-stage reinforcement learning process, it uses a much simpler, single-stage approach. And the key innovation is that it does away with the need for an explicit, separate reward model entirely. The big insight behind DPO is captured perfectly in the title of the original research paper. The core idea is that through some clever math, you can derive an implicit reward signal directly from the language model itself. You don't need to build a separate judge because the necessary information is already there. And the benefits of this approach are pretty clear. DPO is way simpler to implement. Because it's a single training stage, it's more stable and computationally cheaper. It requires fewer models, less memory, and it optimizes the LLM directly on the human preference data without that tricky intermediate step. So this brings us to the central trade-off that developers face in LLM tuning today, choosing between the old guard, RLHF, and the new challenger, DPO. When you put them head-to-head, the choice becomes very sharp. RLHF is the high-complexity, high-cost approach. But if you can master it, it has the potential to yield the absolute highest performance. DPO, on the other hand, is simpler, more stable. and less expensive. And it can achieve results that are very, very close to RLHF with a lot less effort and risk. Ultimately, the decision between these two methods boils down to a classic engineering trade-off. It's a choice between chasing that absolute peak performance with a complex and resource-intensive system or achieving robust, high-quality results with a simpler, more stable, and more direct approach.